Okay, well, let's continue what we were doing last week, which is stoichiometric calculations. Basically, you're using balanced chemical equations to make different calculations. Last week, I showed you how to calculate when you are given an amount in moles and you're asked to find the amount in moles. And then I also went over when you're given the amount in moles and you're asked to find the amount in grams. There's two more types of questions to go through, so I'm going to do those today. The first one is when you're given the amount in mass and you're asked to convert to moles. So the plan is that, again, you start with what you're given, which in this case is the mass. Then you're going to change that to moles by multiplying times molar mass. Then you use your mole ratio. So we'll go through some examples. First, the first step in the industrial manufacture of nitric acid is the catalytic oxidation of ammonia. So they've given you the unbalanced equation. And then it says the reaction is run using 824 grams of ammonia and excess oxygen. How many moles of NO are formed? How many moles of H2O are formed? Very important that they tell you that the reaction is unbalanced. So let's go ahead and start with balancing that first. So if I start looking at the left-hand side versus the right-hand side, I notice that there are the nitrogen, there's one on each side, but hydrogen, you have 3 on the left and 2 on the right. So you remember what I told you on how to balance that. You put a 2 here and a 3 there. So there's 6 each. Then you've got 2 nitrogen on the left now. So I need to have 2 nitrogen on the right-hand side. But now an interesting thing happens because now I have 5 oxygen on the right-hand side. And that means that I need 5/2 on the left. Now, the reason why I say 5/2 is because it's O2. So 5/2 times 2 is going to be 5. That will balance the 5 oxygen on the right. Now, you can do it this way, but of course, you cannot have fractions in a balanced equation. But for myself, I find it easier to do it this way and then just multiply everything times 2 so that you end up getting 4, 5, 4, 6. Okay, so just to double check, I've got 4N, 4N. I have 4 times 3H, which is 12. I've got 6 times 2, that's 12. And the last thing is oxygen. 5 times 2 is 10. And I've got 4 times 1 is 4 plus 6, which is 10. Okay, so that's the balanced equation. So let me clean all that up. 4, 5, 4, 6. Okay, 4, 5, 4, 6. Okay, now it says we have 824. So this is for part A. I've got 824 grams of NH3. And for part A, they want to know how many moles of NO are formed. And for part B, we're starting with the same 824 grams of NH3, but they want to know the moles of H2O. Okay, so first thing that we're going to do is we're going to change the grams into moles. So according to the periodic table, we have NH3, the mass of N, we have 1 atom times 14.01, that's 28.02. Oops, no, that'll be 2. I don't know why I was thinking times 2, 14.01. And we have hydrogen, which is, there's 3 of them, 1.01, so that's 3.03. The total mass is 17.04 grams per mole for ammonia. In this case, I want grams on the bottom, so it can cut with this grams. Keep in mind that NH3, 17.04 grams, and I'm just going to go ahead and write that down here as well. 17.04 grams. So I can cut grams, oops, for ammonia. NH3. Okay. So now I have, for part A, I've got 1 mole of ammonia, but I want to calculate for moles of NO. So now I use my balanced equation. I want moles of ammonia on the bottom, so I can cut here, and I've got moles of nitrogen monoxide on the top, which is the unit that I'm wanting here. So looking at the balanced equation, I have 4 moles of NH3, so that goes on the bottom. 4 mole NH3. And according to the balanced equation, I have 4 moles of NO. 4 moles of NO. And so I can cut moles of NH3. I'm also just going to go ahead and cancel the 4. And then using my calculator, I've got 824 divided by 17.04. And you get 48.36 moles of NO. I'm going to do the same thing for part B, but I need the mole ratio between ammonia and water this time. So I cut grams of NH3. Oops, forgot the H there. And again, I've got 4 moles of NH3 on the bottom. This time I have 6 moles of water. That's a terrible 6. 6 moles of water. Oops. Cut that. I can go ahead and cut this to 3/2. Or you don't have to, I mean, it doesn't really matter, 3. And again, I use my calculator, 824 divided by 17.04 times 3 divided by 2. And I get 72.54 moles. Now, a good rule of thumb, as I've always said, is round your answer to 2 decimals. Okay. Okay, so that's the plan, which is what we did. So you go from grams of NH3 times the molar mass, and then use your mole ratio to get moles of NO. Same thing, but for moles of H2O, and then you get the answers. So the main idea is that you're using either the mole ratio or molar mass. So the last type of calculation is the longest. This is when you're given the amount of mass and you're asked for the amount of mass of a different compound in the equation. So this is going to require changing the grams to moles, using the mole ratio, and then using the other molar mass to calculate back into the mass for your unknown substance. So here's an example. Tin 2 fluoride, SNF2, is used in some toothpastes. It is made by the reaction of tin with hydrogen fluoride according to the following equation. Now you can see that's already been balanced because we have a coefficient here. How many grams of tin 2 fluoride are produced from the reaction of 30 grams of HF with SN? Okay, so again, we start with the data that we're given, 30.00 grams of HF, and we want to know the grams of SNF2. So we're going to go from grams of HF to moles of HF using the molar mass of HF. Then we're going to use the mole ratio to convert moles of HF to moles of SNF2. Then we're going to use molar mass of SNF2 to convert moles of SNF2 back to grams. There's going to be a shortcut method that I'll show you how to do in a second. We're going to do the long way first, and then I'll show you the short way. Okay, first thing, calculating or converting grams of HF into moles. So HF H is 1.01. F, I believe, is 19. Let me double check. Yep. 19, so that's 20.01. So I've got 20.01 grams of HF per 1 mole of HF, and I can cut grams of HF. Next, I use a mole ratio according to the balanced chemical equation. So I want moles of hydrogen fluoride on the bottom. According to my balanced equation, the coefficient is 2. So I have 2 moles of HF, and SNF2 is 1. SNF2, cut moles. Last thing I need to do is to change moles of SNF2 into grams. So I need 1 mole SNF2 on the bottom. And what are my grams? So tin is, light, here we go. 118.71. And of course, F is 19 times 2, which is 38. So 38 plus 118.71 is equal to 156.71. 156.71 grams SNF2, and I can cut the moles. So just double checking, my grams of HF, which I started with, have canceled. The moles of HF have canceled. Moles of SNF2 have canceled, and I'm left with grams of SNF2, which is what it asked me for. How many grams of SNF2? So now I just do the calculations. I've got 30 divided by 20.01 divided by 2 times 156.71. Oops, I did 74 instead, 71. And you get 117. Oops, I can't write with a laser. 117.47. Okay, so now that I've showed you that, when you're given mass problems, there is a shortcut you can use. And it might be a little confusing, so I want to make sure that I go through it slowly, okay? So I'm just going to use the same, let me get to the balanced equation again. Oh, okay, I'll just go back here. I'll rewrite it myself. So I've got SN plus 2HF yields SNF2 plus H2. That was the original equation, okay? So one thing that you can do when you're doing stoichiometric calculations, especially when it's grams to grams, this might be a shortcut for you to use instead of going through the whole conversion process. It only works from gram to gram, and it uses proportions, okay? So what I'm going to do is on the bottom, I'm going to put the, how do I say it? The ratio of reacting masses. And basically what that means is I'm going to put the total mass of all of the substances that are reacting and produced on the bottom, but I'm going to take into consideration their mole ratio. What that means, okay, maybe instead of writing that, I'll just explain what I'm doing. So according to the balanced equation, I've got 1 here, there's 2, 1, and 1. So I could say 1 mole of SN reacts with 2 moles of HF to yield 1 mole of SNF2 plus 1 mole of H2, right? That's what those coefficients mean. But I can convert the moles into grams. So if tin has a molar mass of 118.71, I could translate this into grams. So I could say 118.71 grams of SN react with, and now I have to say, okay, what's the molar mass of HF? I forget what that was, 20.01 grams per mole. But 2 moles react. So if I do 20.01 times 2, I could translate that to mean instead of 2 moles of HF, I could say 40.02 grams of HF. So I'm just changing the mole ratio to a gram ratio. So 118.71 grams of tin react with 40.02 grams of HF to yield. And then what's the molar mass? Oh, I don't have it because it's on the other slide. SNF2, so 118.71 plus 38, 156.71 grams of SNF2 plus, and then hydrogen is 1.01, but it's H2, so it's 2.02 grams of H2. So this is another way to say it. So you're just putting it in mass instead of in moles, but you have to account for the mole ratio. Okay, so what I can do is, shoot, what did I say before? Oops. How many grams of SNF2 are produced from the reaction of 30 grams of HF? Okay, so we have, 30 grams of HF. And they want to know how many grams of SNF2 are produced. Well, if I have a mole ratio between the two, and I can convert that into grams, I can do a ratio. So if 30 grams are reacting and the mole ratio of HF is 2 moles, which translates to 40 grams, I can say 30 grams to 40.02 grams. And then on the other side is my unknown, which I'm going to say X. And the total mass that reacts according to the balanced equation is 156.71 grams. Okay, so the left-hand side is representing HF, the right-hand side SNF2. So it's a ratio between, if according to the balanced equation, 2 moles of HF will yield 1 mole of SNF2, I can translate that to mean 40.02 grams of HF will yield 156.71 grams of SNF2. So that's the relationship here, 40.02 to 156.71. But according to the question, they said, how much of SNF2 do I produce if I've only got 30 grams of HF? So on the top, 30 grams is proportionate to how much? And then you just cross multiply, right? So you would have the 156 multiplies up here. So X, I'll write it on the left, X is equal to 30.00 times 156.71 divided by 40.02. And you should get the same answer we got on the previous page. 30 times 156.71 divided by 40.02. Yeah, you get 117.47 exactly grams. So that's a shortcut you can use only for gram to gram. Now I have some practice problems, which I will go through, and I will do it the long conversion factor way first. And then I'll do the short proportion way. Okay. Calculate the mass of silver bromide produced from 22.5 grams of silver nitrate in the following reaction. Now we see that it's already balanced. I've got my coefficients. So first thing, the long way, I'm going to use conversion factors. So I've got 22.5 grams of silver nitrate, that's AgNO3, and they want to know the grams of silver bromide. So first thing I do is I convert AgNO3 to moles. So Ag is 107.87. N is 14. O is 3 times 16, which is 48. So 107 plus 14 plus 48. 107.87 plus 14 plus 48. And you get 169.87 grams per mole. So 1 mole AgNO3 is equal to 169.87 grams. AgNO3. So I cut grams. Next, I use my mole ratio. So I've got 2 moles of AgBr per 2 moles AgNO3, moles of AgNO3 cut. And then finally, I've got AgBr. So I've got Ag is 107.87 and Br is 79.9. Again, I get these numbers from the periodic table. 107.87 plus 79.9. That's equal to 187.77. So it's 187.77 grams of AgBr per 1 mole. And cut AgBr. I'm also going to cut the 2's out because they cancel. So finally, you get 22.5 divided by 169.87 times 187.77. And you get 24.87. Now, an alternative, what I could do is, okay, the question says I've got 22.5 grams. Sorry, it's kind of small. 22.5 grams of AgNO3. They want to know how many grams of AgBr, so that's X. On the bottom, I can convert 2 times AgNO3 to mass because I've already calculated molar mass. Or you could just calculate molar mass. If you don't do all of this, I mean, then you wouldn't have the molar mass, but you'd calculate anyway. So 1 mole is equal to 169.87. So 2 of that is equal to 339.74. And I do the same for AgBr. 1 mole of AgBr is 187.77. But according to the balanced equation, 2 moles are produced, which is 375.54. So there's my proportion. I've got 22.5 over 339.74 equals X over 375.54. Now, you can use either one of these methods, okay? I don't mind which method you use. If you're more comfortable with the long conversion factor way, that's totally fine. But if you are really more comfortable with proportions, that's fine also. Just make sure that if you do the proportions, if you do this method, make sure you're showing me your calculating of molar mass so that I can trace, if you have made a mistake, I can trace it back to maybe it's a simple mathematical error or something like that. So your proportion ends up being X is equal to 22.5 times 375.54 over 339.74, and that is equal to the same thing. But let's just double check in our calculator. 22.5 times 375.54 divided by 339.74, 24.87, exactly the same. Okay, either method is acceptable. And you can see, yep, there we go, 24.9. Let's do another one. What mass of acetylene, C2H2, will be produced from the reaction of 90 grams of calcium carbide, CaC2, with water in the following reaction? Again, you can see the coefficient in front of H2O, which means it's already been balanced. Oops. Okay, well, we know the answer is 37. So again, I'll do the long way first and then the short way. So we've got 90 grams of CaC2, 90 grams CaC2. We want to know the grams of C2H2. Start with molar mass of CaC2. So Ca is 40.08. C is 2 times 12.01. And let's see, 40.08 plus 24.02. And you get 64.1. So that's 64.1 grams CaC2. You can cut CaC2. Next is the mole ratio. So there's 1 mole of CaC2 per 1 mole of C2H2. So CaC2 moles cut. And finally, the molar mass of C2H2. So C is 2 times 12.01, H 2 times 1.01. So that's 24.02 plus 2.02, 26.04. Is that right? Let me just double check. 24.02 plus 2.02. No, 26.04. Yeah. Oh, I did that right. Amazing. Mental math is not usually that good. 26.04 grams per 1 mole, and that's C2H2. Cut moles. So I've got 90 divided by 64.1 times 26.04, and you get 36.56. Now, if I'm doing it the proportion method, again, on the bottom, I'm going to have the total mass according to the balanced chemical equation. Now, in this equation, it's easy because the number of moles that react for the compounds that we're talking about in the equation is all 1-to-1. So the reacting mass of calcium carbide is 64.1 grams because it's 1 mole. And the amount of acetylene produced is 1 mole, which is equal to 26.04 grams. So they want to know for 90 grams, what's the mass of C2H2? So it's going to be 90 over 64.1 is equal to X over 26.04. And you get the same thing. So 90, sorry. Yeah. 90 times 26.04 divided by 64.1. And you get 36.56. Same thing. Same thing. Okay.